Uh, we'll continue with the normal activities. So our next speaker is Dr. Eric Morales. He's a very important man, but I don't know why he gave me such a short CV. So uh, he is a faculty of Institute of Geology. He has obtained his bachelor degree from Autonomous University of Champingo, master's degree from UNAM, and PhD from Arizona. One of his outstanding research findings is about the new theory related to mathematical and computational modeling of transportation of a tracer in heterogeneous aquifers and in uncertain conditions. So let's invite Dr. Eric so that he can talk about his, he can give a talk about hydrogeological studies in Mexico City, groundwater flow modeling, land subsidence, and deep exploration. Eric, all yours.
Thank you. Okay. Uh, I think this is gonna work. Okay. Thank you, Dr. Roy, for the introduction. The overview of the talk, we are gonna first mention some of the water issues that affect Mexico City, and we will focus on groundwater. And then the talk contains three main parts. One part is referred to how can we improve the knowledge of the heterogeneous nature of the aquifer, and for this we use lithological well logs, and then I will cover some of the work we are doing on land subsidence at a kind of local scale. And then I will go briefly through some of the results that we have been obtaining from collaborating with the Local Water Authority of Mexico City, the SACMEX, through a deep exploration program. First, Mexico City is located in the south central part of the country. The metropolitan area has about 22 million inhabitants, maybe more, maybe less, depending on what the extent is, how the extent of this metropolitan area is defined. But within the political boundaries of Mexico City, this is now called Ciudad de Mexico. We have close to 9 million inhabitants. All this population brings about large pressure on the water resources of the basin. As Dr. Herrera before mentioned, this was a closed basin. So, and all the surface runoff has been already depleted. This is because we are obtaining about 58% of all the water that the city needs from the local aquifer. We are importing about 30% of the needs from other aquifers in other basins, and about 29% of the water volume comes from also imported water from surface basins. Local pumping amounts about twice the natural recharge in the aquifer, and this brings about a piezometric level drop of about 1 meter per year in many areas. This situation and this pressure on the hydrological system brings several problems. One is contamination. As I mentioned, also depletion of base flow and springs. There are still some springs in the metropolitan in the city, but almost all except one river lacks now base flow. And also, because of the geological characteristics of the hydrogeological system, also we have problems with land subsidence. In all of these, for all of this situation, we need to have a sound knowledge of the system, sound hydrological knowledge of this system that allows us to go to analyze the problems in that context, and also to build tools for prediction, groundwater models. When we do a modeling exercise, there are several. It's a challenge in the sense that we need to recreate in some way the natural system. Obviously, we are not able to recreate the whole system. We have to choose some processes that we want to mimic, and we ignore, not by decision, but because of we don't have another choice, other processes. In that situation, if we focus on groundwater modeling, then always our results, our predictions, or our modeling results are affected by uncertainty, by errors, and we would like to account rigorously, estimate those errors in order to be able to say, okay, my prediction is this, and the error that might be involved in this prediction is in this range. These errors may come from field data, measurement errors, but also typically come from incomplete knowledge of the natural system. Typically, we have just a limited amount of measurements. That is combined with the highly variable nature of the natural systems. We can conduct a permeability test at one point and conduct another permeability test 100 meters afar, and the results will be very, very different, even within the same geological unit. So that variability presents also a challenge. And we can also talk about boundary conditions, natural recharge, etc. All the stresses that go into the model. And also another situation is limited information about the hydrostratigraphy. And precisely in this part is the talk that is this section. Before that, we have done another work. I'm not going to visit this in detail, conducting or developing methods for stochastic modeling to estimate mean and variance of the variables that, for example, when we are dealing with a concentration of a contaminant, it would be mean concentration and variance of concentration. And we have also tried to look into how the conceptual uncertainty affects the results through multimodal approaches. But I mean, this could be for a different talk. Here in this part, I will focus on a master thesis work of Priscilla Medina Ortega, trying to obtaining a three-dimensional model of hydrophases for Mexico City. Typically, when we try to represent the system, and mainly when we go to very, very large scale, because of the necessity and the scale that we are dealing with, the system is represented by layers and type of cake layers. But the system is a bit more complicated. And some problems, such as contamination study, more local contamination studies, wellhead protection zones, and land subsidence, needs a more detailed representation of heterogeneity. So with this motivation, we conducted a study to generate a 3D model of the heterogeneity of the system. This work came to start when talking with Tonio Esprio, who is here. He told us he had a large amount of well logs available, and what could we do with those? Here the dots represent the location of the wells. Here is the lithological logs, go from 200 to 800 meters deep. And they have different lithological categories. To do a geostatistical analysis, we simplified this data set, and we defined 4 hydrophases. A hydrophases is a groups one or several lithological characteristics that we postulate that have similar hydraulic behavior, say similar hydraulic conductivity. In that sense, for example, we have lacustrine clay from the top aquitart, which is low permeability, which is hydrophases A. We have a combination of a cemented conglomerate, also a cemented tuff, and some volcanosedimentary porous media, which has a clay texture that also we postulate as low permeability, and lava flows, and also granular material that is a high permeability material. We, based on this indicator formalism, which is one if, for example, if we are looking into hydrophases A, this part of the system would be with ones, and the rest of the system would be with zeros. Using a geostatistical analysis and a sequential indicator simulation, we were able to construct a 3D model of the system. This would be the distribution of the hydrophases. Notice this was obtained with 1,000 realizations of indicator of this conditional indicator variables, and we also computed the uncertainty, a measure of the uncertainty related to that. These plots are constitute the probability of finding a given hydrophases in that area. For example, this is the probability for hydrophases A, the lacustrine sediments. Obviously, in the top part, we have that we find those hydrophases, and then the boundaries are not well defined because precisely of the on the lack of many data. But this type of uncertainty is reflected in this probability. And also, we check how good our simulation was, comparing with the proportion of lithological, the different lithological integrated proportion in the horizontally integrating the proportion of the hydrophases, and comparing with the proportion with depth. The vertical axis is elevation, and the horizontal axis is proportion, goes from 1 to 0. And for example, for hydrophases A, we are able to reproduce this behavior. This is for the 4 hydrophases. And this obviously would need to be combined with hydraulic tests to assign parameters to each of these hydrophases. We actually conducted inverse modeling of 3 pumping tests, but the accuracy or the uncertainty of the estimates were not enough. In order to this problem, to this inverse problem to be well defined, we would need measurements, piezometric measurements in each hydrophases in order to separate the effects, not only drawdown in the pumping well. The next part of the talk deals with land subsidence. This is a map of the ancient lake system. This Mexico City, the line represents the extension of Mexico City, and a maximum accumulated settlement is about 13 meters in some areas, like this one. And this has different problems. The approach to model land subsidence has been, or typically is done in large scale. However, and in the horizontal part. However, number one, when we analyze the flow system and we have an aquitard and an aquifer, due to the large contrast of hydraulic conductivity between the aquitard and the aquifer, the flow lines tend to be vertical in the aquitard and horizontal in the aquifer. In the local scale. Because of that situation, that allows us to look into the problem in a 1D model. In addition, another motivation for this was that whenever we analyze the geotechnical logs that are available for foundations and buildings, we find that the properties are highly variable in the vertical. This, for example, is water content, gravimetric water content, that can we transfer to porosity. And we can see large variation of porosity at very, very small scale. The question is how this variability at such small scale, I mean, we are talking about tens of centimeters, is really important, is really affecting the process or not. So we look into this problem. This is also a plot of permeability, values of permeability tests conducted in the aquitard in Mexico City, conducted by Adrián Ortega and Carlos Vargas. And you can see the large variability of values obtained for the aquitard. And they find a weathered zone, which is fracture, that has larger values than the typical values assigned for clay sediments. So this was also motivation for this. So what we did was to use a 1D model, 1D flow model in the aquitard, and also implemented a nonlinear modeling scheme. This was approach. This approach was developed by Shlomo Newman and collaborators in the 82, and then modified a little bit by David Rudolph and Emil Friend. And where changes, as the sediments are consolidating, they are losing porosity. That's the obvious part of the process. But also, hydraulic conductivity is changing and specific storage is changing. So through these expressions, we compute the new values of these parameters. For example, hydraulic conductivity depends on empirical parameter M, and this empirical parameter M relates void ratio versus hydraulic conductivity in different clays, different mineralogy of clays. This is actually this is a plot that comes in a old geotechnical book, Lambia and Whitman, and 69. So what we did was to consider one parameter at a time. The parameters that we selected to consider random were void ratio, which is related to porosity, directly related to porosity, compression index, which is a measure of how compressible the material is. Also, we consider M, the parameter M, and the hydraulic conductivity. Those were the 4 parameters that we consider random. Initially, we took those parameters random, one at a time, and leave all others deterministic. Berenice, this is by the way, this is the doctoral work of Berenice, which is Zapata, which is right here. And we are finishing an analysis where we consider these parameters correlated. Okay, when we consider one single parameter as random, here we exemplify the case when hydraulic conductivity is considered random. So this would be the type of situation. We postulate some correlation structure for the parameter, and then use Monte Carlo simulations to obtain the results. The red line represents the solution for the red distribution of parameters that is presented in the left, and the blue line represents the average of every gray line, and every gray line is a solution for a realization, and that realization, if we compute the mean, the spatial mean of that realization, is similar to the mean of a realization that produces a different behavior in total settlement. This, by the way, is total settlement. What does this mean? It means that if we use mean parameters, we can be having or committing a definite error, which is in total settlement, which is observed by the difference between the blue line and the red line. And also, the uncertainty is larger whenever hydraulic conductivity is random. And by the way, whenever we look into in most studies that deal with subsidence, they always focus on compression index, which is the parameter that controls how compressible the system is. However, compression index, random compression index, leads to not so large uncertainty, and also the mean parameters could give a very, very reasonable, accurate prediction for this phenomenon. So in this case, one interesting result was that random hydraulic conductivity, turns out might be important for local accurate prediction of subsidence. What we did next? Okay, actually what we wanted to do is to provide a modeling approach for land subsidence. And we couple this nonlinear approach with ensemble Kalman filter. Dr. Herrera assisted us with this. We collaborated with her but to do this. And this was motivated because in Mexico City we have around 100 or so multi-piezometers, and the federal agencies have been conducted measurements monthly, bi-monthly, sometimes more space measurements since the 1960s. So we have a wealth of piezometric data which this data can be converted into pore pressure, and obviously that can help us to calibrate subsidence models. So, thinking in this available information, we say, okay, let's then focus on a modeling and calibration method that can assimilate measurements, in principle, hydraulic head measurements through time. And so we use ensemble Kalman filter. What we do here is start with the simulation. We start the simulation with no data and with a uniform distribution of parameters. Here, for example, the black line represents the 5-year distribution of hydraulic conductivity. This hydraulic conductivity is a bit nonlinear because we are imposing here a sudden change in hydraulic head at the bottom of the system. So mainly this part of the system is compressing. And so hydraulic conductivity is becoming smaller and smaller. Here, this other plot represents the deformation of each element. So the black line is the simulation, but then at 5 years we have measurements. So we incorporate the measurement through the Kalman filter formalism, and now the red line represent the corrected prediction, here the corrected distribution of parameters, the hydraulic conductivity, and here the red one represent the corrected distribution of hydraulic head. And you can see the improvement here around 3 meters. Okay, so we are gonna assimilate measurements every 5 years. So 10 years, and now you can see the red line goes a bit much better, trying to follow by the way, the blue line is the reference distribution, the one that we take as the real or the true distribution. So this is 10 years, this is 15 years, this is 50 years. So you can see that we are able to reproduce fairly reasonable deformation and also distribution of hydraulic head, and also we are obtaining a distribution of an estimation of the distribution of hydraulic conductivity. So that's why we in a large enough period of time is a calibration method that help us to improve the condition of the model. This is the final step for 300 years, and this is the prediction of total settlement. The blue line here is the real reference settlement, and the red line is the prediction of the model. You can see here at the beginning of the simulation the large effect of the improvement when we start assimilating data. The method, the ensemble Kalman filter method is based on several simulations. So the gray lines represent every realization that is also corrected, and the red line represent the average of those realizations. What about, we will not wait for 300 years to have a calibrated model, right? So in this case, what we did was to check how good the potential prediction or of this method would have. So we assimilated only through the first 25 years, and then the prediction extend to 300 years. By the way, this simulation time frame is because this type of processes, I mean the consolidation process, it's because of the small hydraulic conductivity and the slow propagation of pressure changes within the aqueduct, then it takes a lot of time to adjust. So changes that we imposed now will have an effect for many years to come. So in this case, we tested 3 ways to improve the model with only measurements of age. We see that the prediction capability of the model deteriorates with time. If we assimilate also only measurements of K, the prediction capability is much better than the first one. And if we are able to have measurements of K and H with time, the prediction capability is much better. Next and final stage is a brief overview of the deep exploration program. And this was a program motivated by the water, high demand of water in Mexico City, and also for improve the hydrogeological knowledge of the system. This was conducted by the local water authority, and also collaborated the Mexican oil company, Pemex, and also the National Water Authority. In this program, 5 wells were drilled. The first one was San Lorenzo Tezonco, which is right here, almost at the center of the figure. Agrícola Oriental, 2B and 2C, are next to Pozo Michuca. Santa Catarina, it's right here, and Miradores over here. In addition to those wells, there are 4 other wells that are available. These wells, Tulyehualco, Copilco, Roma, and Michuca, were drilled between 2,500 to 3,500 meters deep, and were drilled in 1986, following a large earthquake that has had a big impact on the city. Many people, about 10,000 people died as a result of that. So these wells were built the main focus of those wells was to improve the knowledge of the system in order to build better seismic response model. So that the new engineering solutions for foundations and buildings can be put in place. And these other wells, the San Lorenzo all the way to Mirador, were drilled with thinking on the hydrological implications of this. So we had just a limited amount of cores within the formations. We also had drill cuttings, and we conducted petrographical analysis, micrographs, X-ray, fluorescence analysis, and whole rock chemistry analysis of these samples. The volcanic stratigraphy was described in several publications. One of the first one was this by Jose Luis Arce. And we are also, once the oil company came into play, we had a different quality and a different amount of data obtained from these boreholes. So we are conducting a analysis of this in order to obtain a better interpretation for this. I must comment that most of the documented tools for well logs come from the oil industry. It means that it is mainly for sedimentary environments. And here we have a thick sequence of 2,000 volcanic rocks, which is a challenge to do the interpretation. Even when the logs are collected, they need to be to have some pre-process step, and this pre-processing stage requires defining some standards, and these standards typically are for the oil industry. I mean, sedimentary rocks, not volcanic rocks. So we are trying to. This is work in progress. We are trying to collaborating with people from the Ricardo Castrejón from the Faculty of Engineering at UNAM, and to attack this problem. From the course that we obtained, we conducted a petrophysical analysis. We obtained permeability. Also, we analyzed thermic properties, because at this depth, whenever we want to model these groundwater processes, the temperature is gonna be. I mean, we will need to couple groundwater flow and heat transport in order to accommodate all these variables. One of the things that we are doing is to correlate with the wells that were drilled in the 86 years, and we are also analyzing the hydraulic behavior in these wells and taking water samples. These are, for example, the samples for two wells, the Santa Catarina, which is right here, and the San Lorenzo Tezonco, which is here. These other samples comes from the aquifer from 0 to 500 meters, the upper aquifer or aquifer system, and this. In this case, we can see in the previous one that is the geochemical phases is different from the upper aquifer, and also we conducted stable isotopic analysis. Both wells seems to agree with the meteoric line, which. So the origin is mainly meteoric, but are very, very old waters. For the San Lorenzo Tezonco well, we estimated 14,000 years. For the Santa Catarina well, we estimated 5,000 years. I'm not presented those results here, but we also conducted analysis for trace elements, and everything was fine except arsenic, that it was close to the drinking limit for that. So we and the total dissolved solids are not especially large, 957 milligrams per liter and 1,300 for the other one. So the idea with this is to improve the representation of the geologic and the hydrogeological representation of the basin, and by using the new techniques that we are obtaining. Dr. Herrera commented that the lower volcanic unit is considered as an aquitard. This is the unit that she was referring to, And this unit, actually, there is what we think. I mean, we don't have the hydraulic properties to be sure of that, but the upper part, it behaves like an aquitard, but the lower part is quite productive, actually. I mean, it has several zones which are quite productive. And what we want to, we are also using some seismic information for this area between these two wells to try to obtain a better representation of the local heterogeneity on these units. Yeah, and also combining the well logs. In the end, well, we would like to improve the conceptual model of the system and also the modeling capabilities of this system. No? I want to acknowledge funding by these agencies. Well, actually, the collaboration by Pemex and Conagua, SACMEX, and some grants at UNAM, and also a large list of collaborators. Without them, this would not be possible. Thank you.
Maybe a small question so that we can move to the next talk. But after the next talk, we will have 15 minutes to discuss with you. Anybody answer? A small question.
I do have a question about the model. So the model that you built is a 1D model. Is it elastic or viscoelastic model?
Elastic. Well, actually, it has two parts. One part inelastic and one part elastic. The compression part is inelastic. The recompression part is considered elastic.
Okay, and then so you based your model on a well log, I believe. Is it located in
the 1D
downtown
model?
Yeah, the 1D model. You have like a well log. You showed a well log with water content, I believe.
Yeah. Well, that was used as, say, inspiration, but the results are synthetic.
Okay. So what's
however, to go through real data, it would be really easy. There is a condition in formalism that can accommodate, without a doubt, this type of situation.
What's the thickness of the aquifer that you're considering? Like
15 meters. 15 meters.
Okay.
Aquitard. The
yeah.
aquitard.
All right. Thanks.
Sure.
We'll have 15 minutes after the next talk so that you can keep on discussing. So I would like to request Muthu Sankar to come on stage and give a small gift to our speaker, Eric, on behalf of the Alliance.